homework, finding the missing pieces of the triangles. Okay. So today we're going to move on to some practical applications. And when it comes to applications of right triangles, the hard part is seeing the right triangles sometimes. Now, the first application we're going to talk about is probably the most obvious application, and that's something called a sine bar. Have you guys used any of these in the shop yet or seen them in the shop yet? Sine bar usually comes in two forms, either a 5-inch or a 10-inch sine bar. And what it looks like is a flat piece of material that has rounded ends on it like this. And of course, there's a very precise distance from the center of those rounded ends. It's exactly whatever the length is. So let's say this is a 5-inch sine bar. That distance is exactly 5 inches. So we give this a little bit of a three-dimensional effect here. So it looks something like that. And the purpose of the sine bar, when you look at it from the end, it is used to construct precise angles. So let's say we have our sine bar here. And we can stack up gauge blocks under one end of the sine bar to construct a very precise angle. So the distance from center to center is still whatever that precise length is, either a 5-inch or a 10-inch sine bar. I'm going to use a 5-inch one for this example. The angle that we are looking at creating is actually this angle formed right here. You'll note that that angle is the exact same angle that would be formed. Either of these surfaces is going to be parallel to this, that hypotenuse of that triangle. It would be the exact same angle that would be formed with any of those surfaces between that horizontal. So this triangle that we've created here, the distance from here to here is just that very precise 5 inches. That's our hypotenuse. The other length that we know because we created it with the sine blocks is this side over here, which according to that angle is the opposite side. And of course, the trig function that works with opposite side and hypotenuse is the sine. That's why it's called a sine block. It works with it creates the sides of a right triangle that are involved in the sine of an angle. So let's say that we have a gauge block build up here that is precisely 2.132 inches. What is the angle created here? Well, the sine of that angle equals the 2.132 inches, the opposite side, over the hypotenuse. Now remember, if we're looking for an angle, if we have the sides and we're looking for a missing angle, we solve that by doing an inverse sine. So the angle is equal to the inverse sine of 2.132 divided by 5. So it'll be second sine 2.132 divided by 5, close the parentheses. We get, oops, I got to change my modes again. So let's try that again. 25.24 degrees. So the angle we have there is 25.24 degrees. Typically, we work when we're using a sine block or sine bar, we're working the other direction. We know that we need a certain angle, and we're trying to decide what gauge block buildup here that is needed. So I'm going to call that the height of those gauge blocks X to create a specific angle here. Let's say that I know I want that angle to be 18.32 degrees. And this is a 5-inch sine bar again. What gauge block buildup do I need to create the height X? What height X does it have to be? So once again, I'll write down my function. It's going to be sine of theta equals opposite over hypotenuse. This time I know that the angle is 18.32 degrees. My opposite side is my gauge block buildup. That's X. That's what I'm trying to find. Over my hypotenuse, which is 5 inches again in this case. I put the sine over 1 so that I can cross multiply and divide. Sine of 18.32 times 5 divided by 1. Well, sine 18.32. Remember to close that parentheses again. Times 5, and we can skip dividing by 1 because that doesn't change anything. X is 1.5716 inches. Now you might ask, why did I suddenly go to 4 decimal places here? Well, there's a very good reason. One, this dimension, the 5 inches, because it is precisely machined, I mean, a sine block is machined to at least a 10,000th, if not a 100,000th of an inch. That's not really just 5, that's really 5.0000 inches. Second, our gauge blocks go to the 10th or a 10,000th of an inch. So when we calculate the size of that gauge block buildup, we know that the gauge blocks will go down to the nearest 10,000th. We have to calculate to the nearest 10th or 10,000th of an inch. So anytime you're doing a gauge block buildup, make sure you're taking that calculation down to those 4 decimal places. Now, you guys probably don't have your gauge block sizes memorized. But looking at that, you'd have a 0.1006 and probably a 0.101. And I believe there is a 1.2 and a 3.5 and a 1.00 would probably be your gauge block buildup to create that. It's been a while. I haven't used my gauge blocks much lately, so I believe those are sizes in the mix. But if you have the table in front of you, remember you pick it out. You do that gauge block buildup by starting with the last digit, the 6 10,000ths, and you work your way backwards from there to finish your gauge block buildup. Okay, so the last 2 examples we've done have been decimal degrees. But more common is to have this angle, this desired angle here given, and I'm just going to mark it here rather than drawing in the triangle. That desired angle given in degrees and minutes. So let's say that angle, the desired angle is 20 degrees, 40 minutes. And this time we're going to use a 10-inch sine bar. And I want to know what is the height, overall height of my gauge block buildup. I'm not going to break it down into individual gauge blocks anymore. I just want to do it once so you remember that that's how it could be done. We're just going to find that overall height. So once again, the sine function is sine of an angle is opposite of our hypotenuse. We're going to put in our angle is 12 degrees 40 minutes. Opposite side is x, that's what we're trying to find, and our hypotenuse is the 10 inches. So we'll put the sine over 1. Now when we go to do this, we have to put our degrees and minutes labels in there. So I do 12. And my calculator, I have an angle menu. Most of yours have a degree, minute, seconds button you hit. Put in the degrees, 40. I select the second or the minutes. And then that is going to be times 10 divided by 1. Again, I didn't have to put in the divided by 1. I get 2.1928, that rounds to inches. So there's the height of our gauge block buildup that we need for that. Like I said, that sine bar is probably the most direct application because the right triangle is easy to envision there. It's just right there. Other applications, it might be a little more difficult to envision. And one of those is a taper. A taper angle is found if you were to, well, there's two ways to look at it. You could draw this out here parallel to the axis. The axis of a taper, if it's what we call a right taper, the center of the circle on the large end is positioned in line with the center of the circle on the small end. And if you connected those centers of those circles with a line like I just did there in brown, that line would be perpendicular to any radius of either of those circles. That's called a right taper. So in other words, both sides of the taper, it tapers down equally in all directions. The circles, the ends are centered with each other. So if you have a right taper, you can draw in a reference line here that is parallel to what they call that the line of centers, that line that connects the centers of the circles. And an angle is formed between that parallel line and the outside edge of the taper. That is the taper angle. So remember, for a taper, there are three dimensions we are given. We're given a large diameter, we're given a small diameter, and we're given a length. We're going to assume for the purposes of this example that those are all given in the same dimension, all inches, all centimeters, all whatever. So let's say that up here this is 2.125 inches. And down here that this is let's call it 0.625 inches. And that this length here, we'll call it 8 inches. So we are literally looking at this triangle right here. And the dimensions of this triangle are fairly simple. I'm going to redraw it down here so we can see it a little clearer. This is our angle. This side up here is just our length. That's going to be the 8 inches. Side here is going to be the difference in the radiuses, the radii. Well, we were given diameters, so we have to divide those diameters by 2 to get a radius. So 2.125 divided by 2, that's going to be 1.0625. 0.625 divided by 2. That's going to be 0.3125. We subtract that out, we get 0.75, I believe. Yep. So this is 0.750 inches for that. So I'm going to pause there. Any questions on how I came up with that 0.750? Okay, good. We took the diameters to divide them by 2 to turn each of them into a radius and subtracted the radius. So now our angle there is using the opposite side here is the 0.75, and this is the adjacent side here, the 8. So opposite and adjacent would either be cotangent or tangent. Our calculators don't have a cotangent key, so we're going to use the tangent function. Tangent of an angle is the opposite side divided by the length of the adjacent side. And we'll put in our information. We're looking for the angle. The opposite side is 0.75, and the adjacent side is 8. Now, since we are looking for an angle, we find that angle by doing an inverse trig function. Inverse tangent of 0.75 divided by 8. Second tangent, 0.75 divided by 8, close the parentheses. We get 5.36 degrees. Typically for an angle, it is customary to go to 2 or 3 decimal places, depending on your precision. If you're only going to the nearest minute, basically, 2 decimal places is adequate. If you're adding seconds to it, you should have a 3rd decimal place included. Most of what we do, we're just going to go to 2 decimal places unless the homework tells you otherwise. So again, all we did up there was we took the radius of each end, here and here, and found the difference to get that opposite side, and then used the length to get the 2 legs of that triangle so we could find our taper angle. A huge application, a very common application that comes up often is a V-block. Let me make this a little more user-friendly. That's a little bit better. It's a little off-center, but pretend that my V is symmetrical there. So I'm going to give you the distance from the bottom of our block up to that V is 0.5 inches. The overall height of our block is 2.5 inches. The radius of our round stock is 3/4 of an inch, 0.750 inches. And that our angle in here is 38 degrees. What I want to find is the distance that round stock sticks up above the V block. So this would be if you're going to take a piece of round stock and you're going to machine, or mill, I should say, a flat edge in it, you would set it in a V block like this, clamp it down somehow, and then you would machine that flat surface in there. So you need to know how far above the top of that V block. First of all, the round stock has to sit up far enough that the surface we're trying to machine is above the top of the V block. But we also have to know how far it sits up so that we know what elevation, what Z coordinate to put into our mill. So the way this works, this ties back into a lot of our circle stuff from the last unit. We go from the center of our round stock out. That forms that radius, if I go to the point of tangency, of course, has to form a right angle with the tangent. And if I connect the center of the circle to the center of our V down here, that cuts our angle here in half. So each side of this is 19 degrees. And of course, our radius up here is the 0.75 inches. So what we have is we have two right triangles there. I'm going to redraw this one off to the side so we got a little bit more room to work with it. So there's our right angle. This is that 19 degrees, half of our 38 degree V. And this is 0.75 inches. What I'm interested in here is that height. That is the hypotenuse of our right triangle. According to our 19-degree angle, the 0.75 inches is the opposite side. That is a sine. Sine theta is opposite over hypotenuse. So I have that their angle is 19 degrees. Our opposite side is 0.75. Our hypotenuse is one of the dimensions we're looking for here. So I put the sine over 1 and I cross multiply and divide. 1 times 0.75 is just 0.75. Divided by the sine of 19 gives us 2.3037 inches. So this here is 2.3037 inches. That's this height here. So now we can find our overall height very easily. We have the ½ inch from the bottom of our block to the bottom of the V, 2.3037 inches from the bottom of the V to the center of our round stock. And then, of course, the last piece here is just the radius. That's going to be another 0.75 inches. So we're going to add all of those up. 0.5, 2.037, and 0.75. Giving us 2.5537. Something's off there. 3.5537, sorry. 3.5537 inches. What that dimension is that is from the bottom of the block all the way up to the top of our round stock. To get this difference here, x, we have to take that dimension we found and subtract the height of the block, the 2.5 inches. So 3.5537 minus 2.500 gives us 1.0537 inches. That is our dimension x that we are sticking up above the V block. That is probably the most common, most useful application of these right triangles in our machining application. It's also one that people struggle with a lot. So we'll do several examples of that throughout the next couple of classes. Next, we want to talk about hole patterns. And more specifically, we're going to talk about circular hole patterns. Hey, that almost looks round. I shouldn't sound so surprised when I actually draw something right, maybe. So what we're going to look at here is, let's say we have a given number of equally spaced holes around that circle that we have to drill, whether it's for connecting a flange or whatever we're looking at here. So there's only two pieces of information that I'm going to be given. One is the radius of the circle, so from the center of the hole pattern out to the center of each of the holes. And let's say that in this case that is 2.8 inches. And of course, the second piece of information I have is the number of holes. This is going to be a 5-hole pattern. What I want to find is the center to center distance from one hole to the next. So to do that, I start out, I draw a radius from the center of my circle out to the center of two adjacent holes. So it's this distance that I'm actually trying to find in red there. I know about this triangle, at least I know that angle has to be 360 degrees divided by the number of holes. So there's 5 holes here. 360 divided by 5, that's 72 degrees. So I'm going to redraw that triangle there, larger so that we can break it down. So I know this is 72 degrees. This is the side I'm looking for, the length I'm trying to find. But I also know that each of these sides is 2.800 inches, making that an isosceles triangle. However, right now there are no right angles here. Well, I can cut this like this from that 72 degree vertex to the opposite side. Since this is an isosceles triangle, if I draw that at a right angle, I know that cuts this side here in half. So this is actually x over 2, or 1/2 of x. It also cuts our angle in half. So this is going to be 36 degrees. So what we're going to be working with now is just that triangle. This is 36 degrees. This is 2.800 inches. And I'm going to call this y over here because it's not x anymore. It's x over 2. But I want to find that side y. Well, this is my angle by 36 degrees. The 2.8 is the hypotenuse. And y is the opposite side. So once again, we're hitting a sine function. Sine of an angle is opposite over hypotenuse. We plug in our 36 degrees as our angle. Our opposite side is what we're looking for, that side y. And our hypotenuse is 2.800 inches. Put this over 1, and we're going to cross, multiply, and divide. So it's sine of 36, make sure you close the parentheses, times 2.800, then divided by the 1. I get 1.6458 inches. That's y. So x is going to be that amount times 2. Now, when we multiply this out, there's going to be, actually, this one ends up, it does work out fine. But a lot of times when we take a dimension like that 1.6458, that's rounded to the nearest tenth or 10,000th. When we multiply it by 2, that round-off error can cause some issues. Here it didn't. What we get for x is 3.2916, which is actually exactly double that. But there are times where we multiply it by 2, what we get here, that last digit might be off by 1 because of the rounding on that first number. Here it was, 7, 9, so when we rounded up to 8, we didn't lose much. So it still worked out okay. But if this had been like 1.64575, by rounding that up, when we multiplied by 2, our rounding would have been off on that next number. So my point is here, I'm babbling a little bit, is that it's very important to leave this number here in the calculator. So this number here, leave it in the calculator because we know we're going to have to multiply it by 2. If you write it down like this and type it back in to multiply it by 2, that round-off error can cause this to be off by a 10,000. You guys have a packet to work on. In that packet is page 358 through 361. Now, I realize this is your last class for like 11 days. So I do expect we will, when you guys come back after spring break, we will go over these types of examples again. And we're going to spend actually a couple days. We're going to get into some way more complex examples as well of finding right triangles and stuff in our machining application. So I see it actually just started snowing outside here a couple minutes ago. So with that, you guys enjoy your spring break, and we'll see you in 11 days.